Welcome back. So I'm going to go over the answer to the question and you can see how well you did. All right, so I'm going to tell you which ones are similar, are always similar, and aren't always similar. Rectangles aren't always similar. So this one was a no. All right, that's a no. Actually, I'll just put no next to it. All right, because you can think of, kind of a rectangle that's almost a square. Its side measures are pretty similar, and then one that's really, really skinny. All right, those sides wouldn't be in proportion. They're not similar. So rectangles, no. But squares, on the other hand, are a yes. A yes to squares. All right, we've got 4 90-degree angles, so all of our corresponding angles are congruent. They were also congruent in the rectangle. It just lost out on the sides. And our sides are all the exact same measure, right? So they have to be in the same proportion to the other triangle because we're going to be the other figure, the other square, because we're going to be comparing the exact same two numbers. So for instance, if this one is 10 and this one is 3, well, all the sides are 10 and all the sides are 3. So the scale factor would be either 3/10 if you're going from smaller to larger, or from larger to smaller, or 10/3 if you're going from the smaller to the larger. Right? So squares are a yes. Trapezoids, they're a no. Right? They're not always similar. Matter of fact, I only have 2 different trapezoids here. Even if they were isosceles trapezoids and these were the same length, right, the bases don't have to be in proportion. So trapezoids, no, they don't always have to be similar. Triangles. I hope I made it really obvious with the triangles I chose that this was a no. Right? We have lots of different angle measures and side measures for triangles, so they are not always similar. Right triangles. Thought maybe I would trick you with this one. So for instance, this one triangle here, this would be an acceptable measure. This could be 3, 4, and 5. That would make a right triangle. 3 squared plus 4 squared equals 5 squared. This one, maybe this one is 5, 12, and 13. 5 squared plus 12 squared does equal 13 squared. And notice here that those sides are not in the same proportion. So if I go from big to small, I have 5/3, and that does not equal 12 fourths, and that does not equal, the other side is 13/5. Right, so that's not the same. They're not in proportion at all. So right triangles, that was a no. Let's go to isosceles triangles. So now they always have to have, of course, we have a right angle, and we have the 2 legs here are congruent. Right? Those have to be the same. And these angle measures here have to be 45, right? Because base angle theorem says angles opposite congruent sides are congruent. So those have to be 45 because that has to add up to 180 degrees. So now you've got 3 sets of sides, the angles that are congruent, and these 2 sides are the same. We have 2 pairs of sides the same in each of the 2 triangles. And this one here, so let's just call this A and A because they're the same, and B and B, right? They have to equal, so A squared plus A squared here has to equal the third one squared. They have a very special relationship. And the same thing over here. They have to equal that other side squared. All right? So because of that special relationship for right triangles and the fact that 2 sides are congruent and all the angles are congruent, this one is a yes. All your isosceles right triangles are going to be similar. And actually we'll use that fact in a later lesson. So just generic right triangles, no. Isosceles right triangles, yes. Equilateral triangles, of course we have all of our sides congruent and all of our angle measures are exactly the same. They're all 60 degrees here. And so you can see that you're going to be comparing the same same three sides to the same three other sides, and all the angles are congruent. This one was a yes. If you've noticed, equilateral triangle is a regular polygon with three sides. A square is a regular polygon with four sides. The same property is going to hold for all of our regular polygons, because whether you're a regular hexagon or a regular pentagon, all of your side measures are the same, and all of your angle measures are the same. And you're going to have to add up to the same thing whether you're a big hexagon or a small hexagon. So the sides will be a different measure, but they'll all be the same in the larger hexagon, and they'll all be the same measure in the smaller hexagon, and these angle measures are going to be exactly the same in both hexagons. So this one was a yes. So the types of figures that are always similar are regular polygons, squares. Actually, all of your regular polygons, squares and equilateral triangles, are a type of regular polygon. They will always be similar, and the isosceles right triangles. There's one other figure, it's not a polygon, but it will always be similar, and that is your circle. Right? All circles are also similar. So we'll write down circles even though he's not a polygon, and he's a yes too. They are always similar. Right? Right, so I want to go over one more problem, and that's going to be the end of this podcast. I hope you did pretty well, and if you didn't, at least maybe now you understand why, and you'll remember for the future. And so this, by the way, is going to be a problem for you. Our figures are similar. You're going to tell me the similarity statement. You're going to match up the corresponding parts. And you're going to tell me the sequence of transformations that maps triangle RST to triangle XYZ. Both of those will be multiple choice questions. And here I'm looking for number 2, since we're not on a coordinate plane, just the type of transformation. And you'll see when you look at that question. So I'm going to go past this one and do the last thing. All right, so as shown on the set of axes below, triangle GHS has vertices G31, H53, and S14. We're going to graph and state the coordinates of triangle G double prime, H double prime, S double prime, which is the image of triangle GHS after a transformation of, so now this one is a, T means translation. So XY here is going to X minus 3, Y plus 1, and then we have a dilation with a scale factor of 2. So we have 2x, or xy goes to 2x, 2y. Now, which one do you think we do first? Well, it's probably not the way you think it's going to be. This is called a composition of transformations. And this actually will help you in later classes when we look at transformation of functions. So a composition of transformations, you do inside first, outside last. All right, so that dot there is telling us, this is composition, this is function notation. So this is telling us first, second. Another way this could be written is like this. Okay. So I translate the dilated figure. Once we know that part, the rest of it is easy, right? The tougher part for you right now would be knowing which to do first. Right? In this case, it's the inside first. So we're going to do the dilation first. Right? I'm just going to write down the points. Oh, actually, I have them written right up here. That makes it easy. All right, so we're going to take GHS, 3, 1, 5, 3, 1, 4, and we're going to multiply that. This is our first transformation by 2, our scale factor. And that's going to give us G prime, H prime, S prime, which is just going to be 6, 2, 10, 6, 2, 8. So I'll graph that one. Right, so 6, 1, 2, 3, 4, 5, 6, 2 is G prime. 7, 8, 9 just fitting in at 10. 1, 2, 3, 4, 5, 6. Right here is H prime. And then 2, 1, 2, 3, 4, 5, 6, 7, 8, just about in my writing, is S prime. All right, and I will just try to do this without a line tool because I'm trying to finish up here. There we go. So there's our dilated figure, and now we'll do the translation. All right, so our translation, we're going to add -3 to our x's and 1 to our y's, and we're going to take the dilated figure. And I am running out of space. I'm going to put it a little bit lower, just so no one's confused that we're adding 3 and -1 to G prime, H prime, S prime to translate it. So 6, 2, 10, 6, and 2, 8. And that's going to give us 3, 7, -1. That's where for G double prime, H double prime, S double prime is. And then 3, 7, 9 are the y coordinates. So we can just graph that. So 3, 1, 2, 3, 4, 5, 6, 7 is, 3, 3. Oops, sometimes my eyes scan to the wrong thing. 3, 3 is G double prime. And then H double prime is at 7, 7. So let's see, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. There is H double prime. And then S is at -1, 1, 2, 3, 4, 5, 6, 7, 8, 9. So S double prime. So now we'll connect. And there we go. All right? So just have to make sure you do them in the right order, because it will change the figure if you do them in a different order. And that's the end of this podcast. You can now do the classwork for this part. And then we're going to be looking at triangles specifically, because they have some real special rules for similarity. All right, thank you for watching the podcast. Bye.